Today I'm going to talk about COVID-19 deaths. Just as a bit of background, I teach at a university in Texas called Texas A&M University, which is about the third or fourth largest university in America. But other than that, it's not really that great. My main interest in the last few years, or the last 20 years, has really been monitoring bridges and structures for damage in earthquakes and damage under applied loads. We use very sensitive accelerometers, and we've developed some fairly sophisticated techniques for monitoring the data. Usually we're getting something like 20 million points every 8 minutes, and we do our analysis immediately and then throw the data away and just keep recording it to the cloud. So I became interested in the COVID-19 deaths because I also became interested in deaths in earthquakes, purely to try and work out what was wrong with our buildings that was causing all the deaths. So it was sort of, you had to do one in order to study the other. So today I want to talk about the use of fast Fourier transforms and the generalized Poissonian distribution to study the COVID-19 deaths. It really started when I was looking at the University of Washington, which is the big publisher of and the authority that everyone points to for the US analysis of deaths, and also the stuff from Oxford. And I had a look at their results when it first started 60 or 70 days ago, and the shape of their curves just didn't match what I would expect from ODEs. I've been doing a lot of ODE work with bridges, generally at second order equation with all the terms, which are actually quite difficult to solve. And so I thought, oh, I'll just have a quick look at it. I'll spend a morning and see if I can reproduce what they had. And so far I've been on it for the last 2 months. So someone once said, somewhere in this mess there is sense, finding it is the hard part, which is true. I just want to outline some of the basic theory. I know you're all mathematicians and will understand it quite well, so I'll try and keep it brief. The 3 critical questions was, can we determine the mathematics of the patterns in the daily death data? The guy from the University of Washington, IHME, he kept publishing his results, and then I'd done some analysis and had a pretty good idea of what the death toll was going to be. And he kept upping his prediction and getting closer and closer to what appeared to me to be a much more sensible answer. The other thing that was interesting is the pattern random? Because there are random and non-random elements in the pattern. And we find this in our bridge data, is that we have lots of patterns that they come and they go. They can be temperature dependent. And so we get fairly good at looking at these patterns and trying to work out what's going on with the bridge. The other one that interested me is several of the people that review papers which I've written on mortality and earthquakes have commented about their techniques for doing earthquake modeling, and I've been in and had a look at some of their methods, and they attempt to say that you can subset these areas and do the analysis. And often mortality data really has a sort of defined region that you've got to work within, and subsetting it really can cause you problems. So I was interested in looking at it to see how large an area you had to get to and how compact it had to be, and what were its characteristics before, or so that it would work. So I'll talk very briefly about fast Fourier transforms. I assume everyone understands those. I'm looking at 4 sample areas, the New York State, and the problem with the New York State is it's the one that everyone's been talking about, but New York State is actually really only half the area. We have New Jersey and Connecticut, which make up the New York statistical region. So New York State is 10 million in the city of New York, but the New York statistical region is really about 20 million. The other thing is the data format has been quite interesting because no one uses a consistent publication format. So there's data formats all over the place. The one that I've been using the most is the European Union stuff out of Sweden. Their data is reasonably good. It's a little bit censored. They don't pick up everything, and they make the occasional mistake, but they also respond very quickly to comments and corrections. So they've been quite good to work with. So the fast Fourier transforms, generalized Poissonian distribution. I started using generalized Poissonian distribution back in the mid-90s to late 90s, trying to predict changes in the distribution of earthquakes with time, because the number of fatal earthquakes is increasing with time. It's not constant. In 1840, there was about 4 a year. Now there's about 20 to 23 a year, and there's a definite pattern in it. There's about a 10-year wave through it, but it's within very tight limits. The other thing I use is data normalization and logarithmic transformations. So this is the sort of stuff that I normally do. I'm normally monitoring bridges. We work with the thermal layer because our accelerometers are so sensitive. The thermal layer is Gaussian, which is really, really good. We try and avoid any other loads that come on the bridge, and we listen often enough that we can basically throw away the loads. We do go in and look at them, but we don't really use them. The other thing that it allows us to do is the one on the right is the contour plot, and there you can see the frequency peaks. So that's our normal stuff. So New York has been in the news because they really got hit hard by the COVID. That New York has a huge influx of tourists and those coming in from Europe. Europe has been hit really, really bad in Italy, which I'm sure you're all aware of. So this is just New York. I was just showing you where it's located. Its major urban area is down the bottom, but the major urban area is not just in New York, it's also in New Jersey and Connecticut. And the other thing that's interesting about this is that the density is really quite high, quite significant. New Jersey is right below New York, and you can see this sort of major urban area which spreads across 3 states. And the problem is that the same problem we have with earthquakes is where earthquakes can spread across jurisdictional boundaries, and we run into problems that this city isn't talking to that city, and trying to get data can be, really, really tough. So getting data in China is very hard. Getting data in Indonesia is not quite as hard, but it can still be quite hard. And then Connecticut is a little puny state, but Stanford and Greenwich, down in the bottom left-hand corner, are really still part of New York. So that's the New York statistical region. It is really, really quite large. The problem with just looking at the New York data that's published for the state is that it only represents about half of the data. It doesn't represent the full data set. So I was interested in, really, from earthquakes, and also from the bridges, we're interested in the quality of the data. So I can go back in and look at the quality of the data and see are there variations in it. Because we do bridges the oldest bridge that we've done is about 2,000 years old. We've done lots of bridges in Italy. We've done lots of bridges in England, done the 7 bridges. And now the main ones we're studying at the moment are in Iowa, in the middle of cornfields. So the red just shows you, again, that urban area that I was really interested in. So one of the things that you learn with bridges is just to normalize the data. So I don't really care that much about the normalization constant. In this case, this is the US data from the 70th day. By the 70th day after the first death, we're starting to get a reasonable number of deaths taking over. Now what you see, the blue line is the cases, they're normalized. The orange line is the deaths. So I could run a correlation analysis. I've got a Fortran program for doing correlation, and that went in and basically said, look, there's about a 7-day lag So that's offset 7 days. So you can see that the pattern pretty well matches. So at this stage, we can pretty well tell you what the next week's going to be like in terms of what are the bad days going to be. So that the deaths lag the cases by approximately 7 days. Now remember, this is for the entire United States, okay? So it's not 100% accurate, but it's not bad. I can at least tell you it's likely to go up, it's likely to go down. I used the New York Times data because they collected data for the states, and I also used the Worldometer data because that was really quick and easy to get to, and they update it all the time. So I'm interested in the cases which are recorded, the deaths per day, and then particularly with the deaths, as soon as you've got this number of deaths, you're really going to start taking the logarithm of them straight away, and you're really using log data. So I started with the SAR model. There's a couple of guys out of China, one from Chengdu, which is down where the big earthquake was, the other one from the big Chinese university in Beijing, and they published a paper which I got hold of. And I've looked at Brouwer stuff, and I've looked at Zeng stuff, Beng stuff, but I like the Chinese paper because they published some raw data on the results, which I'll show you in a minute. They also had a special compartment just for deaths in their model. So it saved me having to try and work out how to amend, I think it's Feng's her name, their model for that. So I really dislike using Mathematica or R or those. I mean, I use them, but I don't like using them. So I coded it as a Fortran analysis, so because it'll run quickly. My other idea was other people would come and ask for it, and they have been. I've had people from all over the world coming and asking for the program, so I just give it to them. The other thing that I did was with the ODE analysis is I've been using it with a Wiener process and a periodic function. So the SAR model, models are really simple counting models. When you look at them, they're really just a detention-based model for flood analysis, water supply modeling, pandemic modeling. They're all really the same. The one that I took was Peng's model, and I'm going to talk about that a little bit. And I was interested in his explicit depth compartment. It's easy to code in Fortran. It only took a day or so to get it running. And the other beauty is there's a drawing package, Discipline, which goes along with the Fortran, which allows me to do the drawings fairly quickly. So here's Peng's model. He's got the extra compartment for death. And he's also got this insusceptible one, which is actually turns out to be quite interesting to watch. And then he has 6 variables, and they publish the results for those variables in their paper for China. So I started out using their published data, but then moved away from it because it actually was one or two elements of it appeared to be very, very conservative. So if you have a look at an ODE model, and I take one from Brouwer's book here on the right, the blue line is his S compartment. So I entered all the data and then fitted a curve to it. It's a 4th order polynomial. It fits, really, really well. So it's smooth to the sort of 4th differential. So if you start looking at that, the problem is that the SAR model is giving you a very smooth model, but the real data is not smooth. The real data is going all over the place, and trying to understand what was happening with that was a lot like trying to understand what was happening with the frequency components in a bridge, because we find our frequency components in the bridge are highly temperature dependent, which none of the engineering models really allow for. They just assume everything's going to be standard. So this is his first fairly standard equation. The only difference is they've added that alpha ST at the end for this insusceptible compartment, which is, I don't really think there is such a thing as an insusceptible person. I think it's just someone who's basically protected from the protected from the disease. So the smoothness was the thing of interest. So I used that smoothness to go in and look at all of these equations. So the alpha is the one that I've been using to try and calibrate it, because that was one of the ones that they'd used to calibrate it in China. The Chinese had an alpha of 0.1. Basically, an alpha of 0.1 means that your disease dies out within about 10 days. So I played with it a bit to get a reasonable fit. Now, my initial reasonable fit was really only to 20 or 30 days of data, and that was really low death tolls. So my initial estimate was 0.047. The current estimate is about 0.051. So that's reduced the death tolls a little bit, but it seems to be working quite well, it was reasonably easy with their model to start predicting. It'll predict 200 days in advance, and then track it against the actual deaths. Then I kept looking at the IHME model and the Oxford model and wondering, why are they so far away from the reality? Why are they amending it all the time? I mean, it wasn't that difficult with the Chinese to get a reasonable estimate. So here's the exposed population. The interesting one is the gamma. Peng used a beta of 1. You can either do this as a discrete time step, or you can do it as an ODE model. I used the ODE model. The only problem I had with it was that it picked a variable time step. It was trying to be highly efficient, and I really wanted to use a time step of just a single day. I didn't care that we were trying to, the original code was trying to solve things very efficiently, so it might take a 2 or 3 day time step, but I actually wanted the data in between. So it took a little while to unravel the code and make it so that it basically stepped forward 1 day at a time. So some of the graphs you'll see are before I managed to unwind that. Now the beta of 1 is what the Chinese used, and I haven't changed from that. So they use the pretty standard definitions, the rate of change of infection, all that sort of stuff. And they introduce a quarantine compartment. So this is the extra stuff that the Chinese added in the fatal compartment. And then they started to publish some data for the early Chinese results. The Chinese results are interesting, but they appear to me to be doctored. I think they had the fast Fourier transform results just don't look particularly normal for the Chinese stuff. So it looks like someone's taken their hand to the pen and run them down a little bit. But this gave me some ideas for what were the ranges for the kappa and those sorts of starting points for the finite element, for the ODE model. Peng also provided an estimate for the basic reproduction number, that's what they called it, and they said it was time dependent. So this shows you the US data up until about 20, 25 days ago. This is one of the early plots, and it shows you the ODE solver using the standard 0.0515. Now, the reason it looks a little bit jagged is because this is the one that used the variable time step. And at the time, I wasn't particularly paying that much attention to it. I was more interested in getting other programs running, but I've since smoothed it out, so it is actually smooth. But once I had this running, I could then compare the shape of this to the shape at Oxford and the shape at the University of Washington, and the two shapes didn't agree at all. But the current one estimated that we would pass 100,000 deaths, I think, by the 26th or the 27th of May. So this model runs reasonably well, but I was really interested in why have we got these quite periodic functions evident in the data. And remember, I spend most of my days just looking at periodic functions in much more messy data than this, out to 1,000 hertz. So I was interested in what was the underlying function and what could it possibly point to. But this shape points to the smoothness assumption in the ODE model. So you can just work through. You start out with the S being smooth, and from there you can just do a little bit of simple mathematics. And it says that the whole thing should be smooth. The only problem is the real data isn't smooth. So I was interested in what was the underlying distribution in the real data. One of the data distributions that I use all the time is the generalized Poissonian distribution, because it works for earthquake data. That was just the first one I grabbed. It's not that I couldn't have grabbed others, but this one I have coded in Fortran. It's really quick and easy to use. It's a minute's time to actually use it. And so I looked at the data and I worked out a method of dividing today's result by yesterday's result and getting a ratio of the change in deaths for each day moving forward. And from there, I started to ask what sort of process, underlying process, is driving this this underlying pattern. The problem is, when I first started looking at it, I only had very limited data. We hadn't even got to the peak, so I assumed in the beginning there was some sort of random process, and I started out putting it on Lambda. So I'm going to talk about the results, and the Chinese estimates actually were quite good for getting the first model. Other than their estimate for alpha, the ODE model is, I'll talk about that very briefly, and then I'll talk about the overall results. The Fortran model was developed for much slower computers, and so that's why it took the variable step. They want to solve things very quickly, whereas I was interested in much finer detail. So this shows you the Wuhan calibration data. The interesting one was alpha. An alpha of 0.172 basically will extinguish your pandemic within about 5 or 6 days, which is what the Chinese said happened. But there's no way it extinguished that fast. Even Texas is not able to extinguish it that fast. And then the other ones are just estimates. So here's the main Fortran code that goes in. This is the set of equations for solving it. And then it's quite easy with those to plug in some of the changes in gamma and those sorts of things. So I use the Intel Fortran compiler, Visual Studio. It's just a fairly standard package. So I've been plotting the results since it first began. So the grey dots are the 0.047. That was the first estimate. And by the time we got to about day 40, we were looking at a fairly rapid climb if it had stayed on 0.047. The only problem is that by the time you get to day 40, you can't distinguish between 0.047 and 0.04015, etc. The curves just haven't split from each other. But it was by about day 45 that I worked out that 0.047 was a little bit high, and I started to calibrate it back. And now I tracked to 0.0515 and 0.0525, and then you can see the blue dots is the EU data, the brown dots is the NY New York Times data, and the two track each other, but there appears to have been some lost data somewhere between day 40 and day 50 between the two of them. But you can see that the two sets of data at the moment are tracking along alpha of about 0.0525, but they're crossing over. They're slowly dropping. So it's slowly dropping with time. The interesting thing is we're really fighting two battles in the US. You've got the New York areas coming off a high, but you've got 17 of the other states which have got different characteristics, which are slowly starting to make up for the deaths. So I actually think the US is coming back into a second wave. Now, I don't know if it's going to be a big wave, but states like Texas are not getting better, they're getting worse. So this was just what I was interested in. This shows you some sample output from the model. You can see the day, that's the model telling me what day it's calculated to. So that was the early stuff, and then I went back and amended it so that we're working on a single daily time step. So again, this is the one I became interested in for trying to work out what sort of pattern was happening. And before I actually got to this stage, I used fast Fourier transforms. We use fast Fourier transforms for looking at lots and lots and lots of stuff. So it's just a standard way that we look at data. So I was interested in, I had a look at it. And so what I developed that idea of work out what the attack ratio is. How much is the number of deaths changing per day, make it a ratio, and then take the log of it, because it spans quite a significant number, or significant group of numbers. And like most fatality data, you end up having to move it into the log space. And then I had no idea if it was going to fit the generalized Poissonian distribution or not. It was just a simple assumption of it's very easy to put it into that model. And it turned out it actually, the fit wasn't great, but the fit has been getting better and better and better. And I realize there's lots of problems with the GPD model. There's lots of other models to use, but it's just one that I've got coded. And I was really interested in, with the GPD model, was it getting worse or was it getting better? Right, so you look at that, the data, which is highly random, or appears to be random, and you really want to know is, are we going up or are we going down? So that attack rate ratio, the graph that you see there, the blue line is the actual fatality data, the brown line is the GPD fit, and then the zero in the middle, zero means that you're neither increasing nor decreasing the average attack rate, so that you're just moving along at the same number of deaths per day, nothing's getting better. But you know that the positive side means that you're basically still increasing. And if you have a look, the bulk of our distribution is on the positive side. That around about -0.3 to -0.05, that shape shows up throughout the different data sets that you see. This is a fairly consistent pattern. In this case, the chi-squared is 6. The chi-squared started out at about 28, and it's moved down to about 6. That's the other thing that happens. Usually we find that the chi-squared comes from, you might have it in the 0.6 bin, you might have a 1, or a 0.75 bin, you've got a 2, and they really start to throw a wrench into the chi-squared calculations. So the GPD data does represent the US data. It is a solid block. The representation points to the lack of smoothness in the fatality data. And as we've increased the data, the chi-square value has improved. Now, the question that I was interested in is whether these results are correct for small regions of the United States, because it's very easy. I took the Fortran program, and I've been amending it so I could do each state and do all sorts of things, do each of the countries around the world. And really what I do is I play with it through Excel and those sorts of things to work out how to code it in Fortran and then to move in and code it. But I want to make sure that it's going to work before I start coding it. So the thing that I was interested in next was the Texas deaths. And it appeared for a little while that the Texas deaths were starting to trend down, but they're not. They're now trending back upwards quite badly. This is yesterday's plot. Today's plot is even worse. And so I knew the US data was GPD, so the first question I asked is, Texas is a state by itself. It's got no urban areas that cross into other states, so it's really just one representative block. It has very similar land use patterns. They waste land like crazy in Texas, so they're more like, say, Cessnock or Maitland or places, or not even Maitland, but they spread everything out. They're really, really not very dense, which I think is why they're such a slow build-up for the disease, is that they self-isolate just by the construction, but it is slowly moving upwards. Really, I think they're about to. I think they're in for a really bad shock in the next few weeks. So this is the results for the GPD. The chi-square is not brilliant at 12, but it's because we've only got limited data. They're only up to 50 deaths per day. So it will get worse as they get going. But essentially, the GPD appears to work as long as you've got the fully enclosed urban areas, that your state is not part of a much bigger complex. So I wanted to start with the New York results, and they didn't work. New York State by itself, the GPD just doesn't work. It's not a distribution. You're probably gonna. I will probably have to go back and have a look at one of the other distributions. I just haven't had time. It's just been quite busy. As you can see, the chi-squared is really bad. Most of it comes from one bin. So I then went and looked in at the New York statistical area and said, okay, if we just treat that as an area, we know it's one large urban agglomeration. There's a little bit of Philadelphia added into it, but I mean, 500,000 people in Philadelphia is not going to blank out 20 million people. But the New York, New York State, which had 20 million people, but only 10 million of them lived in New York City, really didn't have a nice balance. So you put the three areas together, Connecticut, New Jersey, and New York, and you come back to the GPD. You come back to the much closer to the national fit. Now, to me, this is just interesting, guys. I'm not standing up and saying this is exactly what happens. I just go in and enjoy looking at these type of things and seeing what can I predict and what can't I predict. The analysis using the GPD doesn't work on New York State being considered as a single entity. I don't think you can make an SAR model for just New York. I don't think that it's going to give you, if you've got a proper model, I don't think it's going to give you one that's going to work very well. So my first hypothesis back in the early days before we got to the peak was that the variation was due to some sort of random process. So I put a simple Wiener process in, and you can see the this is the smoothed one. Do I have the? Now you can see the Wiener process. The Wiener process does not look anything like the raw data. It brought in some random elements, but the random elements didn't do anything like what I expected. So this is when I'm at this stage, and so the first thing you do is I want to understand what's inside these curves, what's inside this periodic function, and by this stage I'm just getting enough data to start looking at it and to start doing the fast Fourier transform. So the first thing you're going to do is just plot the data, do a log plot, do a linear regression on that, get the residuals. Then you've got to decide how long a binary vector you're going to use. I thought, well, we're going to be in this mess for a long time, so I'll go out to 512 because it's either 256 or 512. So I'll go out to 512. So it means that the zeros are padded at the end. Turns out that hasn't hasn't really been a problem. So what we end up with is a fast Fourier transform. I look at these things all the time, so I never go in and actually recalibrate them because I'm only looking for the patterns. I'm not really interested in the numbers. But if you go in and actually look at it, what we have is a periodic function which is about half a week. We have a periodic function which is 1 week. We have a periodic function which is a fortnight. We have a periodic function which is just over a month to 6 months. So there is a cyclic pattern in there. The terrible thing is the cyclic pattern is common across all of the countries I've looked at. Now, I've done all 202 countries, but some countries have very limited death data at this stage, so the pattern really hasn't started to come out. The interesting element is that the peak on the left-hand side is actually a functional relationship to the total deaths, so it actually gives you a nice estimate of the total deaths. So at this stage, I know I'm looking at a periodic function. I know it's got about a week on it. And I know from, I don't know if I got the next plot. So here you can start to see, these are early ones. This is for Australia, really in the first couple of days. And then you can start to see the patterns develop with the week, the fortnight, and the month. The same, here is here is the United States. And then the pattern develops, the same pattern slowly develops. So I do all 202 countries now. So I simply picked gamma. It seemed to be a good starting point. I went in and I put a very simple sine function on it. The sine constant basically gives me 7 days. And that's the result as you currently see it. Now, I haven't been in and been matching all of the constants at this stage. I really wasn't that interested in it. I was interested in, can I at least get a close approximation to what's there? There is a 7-day pattern in it. The deaths do drop during the 7 days. There is a low day. This is not a perfect representation of it. It will get better, but it's certainly better than any of the others that I've seen. And it means that when someone tells you, oh, the deaths have gone down for the last 3 days, you can just look at them and say, yeah, they're going to go up for the next 3 because you're in the wrong part of the week. And you notice that particularly up until the 49th day, it's picked up, this pattern has picked up those bunches that aggregated around. Now, I've got a particular height on the sine function, and obviously I've got it wrong. I need to fix the alpha and a couple of other variables to try and get the top to bend over faster. The only problem is this is the US data, and in 1 day they added 4,000. So that high point that's at 5,000 is really extra data that New York came back in and added in on 1 day. So this is really not a true point, but the rest of it is not too bad. So the daily death data appears to have a periodic function in it, and that's what I'm interested in, guys. I look at periodic functions. They're really what I find fascinating. The rest of it is interesting. The first hypothesis I had is that function is a Wiener process. That's not correct. The second hypothesis is periodic function. I've got one element in the periodic function, and I'm sure it's going to need more elements, but yeah, it'll take us a lot more data and also looking at a lot more countries than I've looked at. But really before I can code it in Fortran, I've got to play with it and work out what have I got to code so I can do all 202. The beauty of the Fortran is to be able to do the 202 very quickly. It takes about 5 seconds to do them all, but you've got to work out the method. It's the same way with bridges. We get to a certain stage, we look at what the analysis tells us, and then we come back and okay, how are we going to code this so that we can do it on bridges all over the world? So this ODE program is actually quite simple. It's only first order. The second order general ones that I use normally on the bridges come from NASA. I'm of the opinion that the GPD analysis may not work. I don't think you can put SAR models on partial urban areas. Now, I could be wrong. It's just an assumption. It's just looking at this data. But the SAR model that everyone is using needs to be amended to allow for this variation in the deaths. And it'll take a while to sort it out. And what I've done is not perfect. I'm not a great statistician. I just ask questions and try and look at data and understand why does someone say this is going to work. I have limited faith in some of the models that are out there. I don't have any faith in this one other than the fact it's a lot of fun to play with. And I've been introduced to a great bunch of guys who don't yell at me too much about writing the either email to say this is what we've been finding. So if there are any questions, I'm quite happy to answer them, because I come in at exactly 50 minutes, which is exactly what I was told I could talk, which is the longest I've talked in like 6 months. Any questions?
I think so. I think that would be what I would be looking for. We'll see what others.
If anyone would like to ask a question, you should be able to unmute yourself now and ask away.
Hi, this is Harry. Can you hear me?
Yep.
Just wondering about the effect of interventions. I mean, this is assuming a distribution goes throughout the whole sequence. There have been interventions such as social mixing, quarantining that have come in halfway through and 3/4 of the way through the data. Have you got any thoughts about that?
Yeah, I was expecting that the interventions would cause the GPD to move into the negative region. Because those interventions take a long time to actually take over, I was expecting to see a gradual change from a positive sided GPD to a negative sided. But what I actually think is happening in the United States, and remember, I've just done this for the United States. I haven't recoded in Fortran, so I can do all 202 countries in one go. That'll take me a few more days. The United States thinks that they've conquered it and that they're going to be able to come out of it. But I actually think what's happening is that New York is getting better because they've been really, really hard on it. But about 20 other states are actually coming up. So even though we have the interventions, and they've stopped us going to like the 3 million deaths per day that you could get if it just ran rampant. That we're still got this sort of slow positive growth. Now the attack rates are really, really closely centered about that log of 0. They're just scattered about it, but they're just on the positive side. So if you look at Texas today, for instance, they had the highest death toll that they've had since the start. Texas is really, really scattered territory. It's if I talk about Cessnock and places like that, or say Barham or places like that, it's really, Houston and these areas are really scattered out. And so they have social distancing built in. So it's taking a longer time for the virus to sort of work its way through the population. But unfortunately, Texans are heavily Republican. They refuse to wear masks. They want to go to church. They want to put their kids back into school. They're really opening up. So I think you've got two sides of the country battling each other, a side which is getting better and a side which is getting worse. And so I had hoped the GPD would go negative by now, but I think that the two sides are battling each other. I haven't looked unfortunately, I haven't coded it fully into Fortran, so I can look at every state and can look at every country. What I've been doing is just developing the methods, and then Hassan came along and said, "Oh, can you give us a lecture on Friday?" It's Friday in Australia, isn't it?
Yeah, that's true.
And so I spent like the last 2 days preparing the lectures, so I haven't done any more. And I'm not saying this is the correct answer. Okay, I'm just saying this is interesting to look at. Normally I should be looking at bridges, and my friend in England that I work with is yelling at me, telling me not to waste my time on this. So this is just a little bit of fun.
Fair.
Does that answer your question?
Where we see a lot of quite a dramatic fall in certainly a number of cases, then you would think you wouldn't have that gradual decline. And I think it's because of the quarantining, which has been quite effective. It takes out the pool of infecteds from the SAR model, if you like.
Yeah, the only problem is that the model takes a long time to, the model has definitely fallen over. I mean, we were well on our way with Donald Trump to having a spectacular breakout, and you know, the states coming in have quashed it, but they half of them have quashed it really well, half of them haven't. And I think those half that haven't are giving us this sort of upward pressure. And so the attack rate is just slow, is staying about the same. It's not changing. And now, if you had a real breakout where you had no quarantining, then the attack rate would go through the roof. It'd be really off to one side. I doubt that it'd be GPD any longer. It'd just be humongously bad. But we're seeing that in Texas. Texas had the two biggest day increases yesterday and today, almost a vertical line compared to what they've had before. So one of my friends is actually, he's an epidemiologist, and he's doing all the work for the state, doing their modelling. So I sent him a note this afternoon after I plotted the Texas data and sent him the graph, and I said, are you going to tell the governor we have to go back into lockdown, or does someone else get to do it? Because they're not going to be happy, because these guys are real Republicans. They think that the virus can't kill them. Any other questions?
This is Harry again. Nobody else is asking questions. I guess I saw a lecture on about analysing data in Wuhan, and the conclusion, certainly one conclusion, was that social isolation isn't enough. It gets you an RT of about 1. And once you apply effective quarantining, certainly in Wuhan, it came down to about 0.3. So maybe that sort of tailing off is because the social isolation, whilst it reduces the mixing, doesn't actually affect the pool of infected people. But until you get a grip on the infected pool, then you're really going to just sort of piddle on ad infinitum, more or less.
Oh yeah, that's okay. I have some friends in Wuhan, so I've visited there because I have 2 adopted Chinese daughters, so I've been to China several times. Wuhan is a lot more like New York than downtown Sydney, and Wuhan are very, very similar. Wuhan doesn't have the skyscrapers, but it has tremendous density and has people living in very close quarters. If you don't start doing testing and isolating those infected people, then you've got a real problem. The Chinese, I mean, from my few trips there, the Chinese can really shut a place down if they want to. They're very, very good at it. But the FFT for the Chinese just bends over too quickly. Even when you're doing testing, you couldn't have picked them all up that quickly. So their death toll is a little bit underestimated. But yeah, no, I agree that the United States is just not doing enough testing to get these, to isolate out these people. They're allowing the infected people to continue wandering around. And I mean, Texas has got 20 million people, and our testing rate is abysmal. Did that answer your question?
Sorry, I unmuted myself. Yeah, that's great. Obviously, a lot of food for thought, and I guess I'll get back to the data and have a look at it myself and try and run your Fortran programs.
Well, just send me an email and I'll send it. And I'll send you the code.
Okay, thank you.
Yeah, if you don't have an Intel Fortran compiler, because if you're doing COVID-19 work, they'll give you one for free. So you just have to go onto their site and apply for it, and they'll give you a license within a day. So
Oh,
that's
right.
a good. Otherwise, it's going to cost you $200. So you just go in and tell them you're doing COVID work, and they give you a license.
Okay.
And it's a really good compiler. There's no problems with it whatsoever. Got a lot better than our days when we used to go to those. Remember those punch card machines and don't bend the punch cards?
Remember, particularly if you dropped a box and then you have to resort or sequence your cards. That was great fun.
No, it wasn't. You clearly didn't drink enough beer.
And what stage is the GitHub project now? Can we access and use the code, or it's?
Yeah, I'll put the code on GitHub in a day or over the weekend and send out a link to everybody so that they can download it.
Great, thank you. Any other questions?
Because you got to remember, guys, it's 1 o'clock in the morning in
Exactly.
America.
You'll have a good sleep tonight.
Well, I've been up for like 20 hours, so I'm just a little bit tired.
I see if there are no more questions, we'll let you go. And thank you very much for your very interesting talk and project you started up. So it's very promising.
Well, I hope I didn't bore you too much. And to me, this was just a labor of love. I just wanted to understand what was going on. And yeah, it was, yeah, it was just a labor of love.
Thank you. It's very nice.
Thank you. It was
Very
great.
kind of you. Thank you very much, everyone, and have a good Friday afternoon. I hope you'll be in touch with John if interest persists. So thank you.
Thank you, John.
It's fine.
Thank you.
I hope I didn't bore you too much.
Thank you. Bye-bye.
Bye.
Bye.
Bye-bye.
How do I get out of here?
Hassan will let us out.